All right, so I'll skip a little bit. So this is the SLS technology. These are the kind of machines we use. They are EOS German equipment. I'm pretty sure you're aware of what is SLS. And briefly, it's basically a powder bed a technology where we have nylon powder stored in the two bins over there. And then there's a coater that will take the powder from one side to the other, and then the laser comes and sinter the part. So basically similar to what metal is, but the base material is plastic. So the key thing is, how do we design for additive? Because you can't just simply take a part that was intended for an aluminum bar or aluminum plate and just have the file and print it will work. The material characteristics are different, accuracies are different, so you have to be aware of that and design for this. So the method we use for designing the parts is we use topography optimization in most of the cases. So in this case, for example, we're building a wire gripper. So we need to grip a wire. So the part at the very bottom here is the profile of the wire and the location of it in space. And the green side is the counter flange that has to go on the robot. Now, what we do after that is that we create a design space. Basically, we tell the program, this is the boundaries where we can build the part. And then we apply the loads on it. We say, okay, we need deflection in that position. We need the loads of gripping at such and such. And then we let the program run and gives us some geometries. We analyze the geometries, and we pick the one that makes more sense from deflection and stress requirements. We then take the part and finish it off to get rid of the sharp edges on the topography results, and then we get that product out of it, where in this case we just printed 2 of them, and that's the physical brick gripper running on a machine. So that is the overall concept of how we design. We want to get the least amount of material to deliver the objective. We do that for 2 reasons. One is obviously the weight reduction, and secondly because of the cost. So the less material I put, it's less cost for the customer. So for 2 reasons, we try to optimize to get the best result. We do that with mechanical components. So this was a bracket in a packaging machine. We did the same result. We integrated some air channels in it, and the result was this one, and it's been used in an actual machine. So that customer used to have an aluminum block and replaced that block with our parts because it was lighter, cheaper, and he didn't have to order 40 or 50 at a time. He can order when they need. They have to plan it 2 days in advance, and they have it. These are the first example of end-of-arm tool we built. It was built for a company called Langen. It was picking crackers. And again, the challenge there was, how can we get a part that is for that weight? Because we had to have change parts. We had to have a very limited height that we can comply with. So we developed with this solution a quick connect. The blue piece here is a quick disconnect, and the 2 yellows can be replaced with different parts and so on. So that was the first project. The reason they picked that project was because they were stuck. They started physically build the tool, and they were way out of range. We visited them a few days earlier, and they just called us in, and we ended up having our first end-of-arm tool about 4 years ago. This is how it looks from the inside. So one thing else, one of the other variables, other tools we built for the same project was this bigger manifold. And to make sure we achieve the required resistance for it, we needed more material in the center where the flange is. So there were some load cases where the part would be hit from that angle, and this will create some moments around that the core of the tool. So we reanalyzed, and we ended up adding some inner structure to the part to strengthen it that otherwise wouldn't be possible with any other technology. So it was simple analysis. You build the core as a design space. You put the loads and got the structure in. Sometimes we do tools. This was, again, originally a body made out of aluminum machine for bearings, and I will show you the tool in a minute. But we did the same thing. We ended up with this structure, but we couldn't have this structure here. It was serving in a food environment, and we needed to close the surface, so we added a skin to it. And this is how it looks like after we've done it, with just covering all that topography with a 2 mil thickness. We end up with a tool looking like this. As you can see, there are lots of components, mechanical components, bearings, and so on. Obviously, we are talking with SLS about accuracies in the range of 100, 150 microns, sometimes 200 microns plus or minus. That won't work for a bearing. If you want to push a bearing through, I need a lot more, a better accuracy. So what we do is that we leave here, you'll notice here some little bit of white material. This is the core material. So we finished the part, we took it to a CNC, and we machined the bearings and we pressed them like you normally do. Now, also, we developed some experience with the machining, because it's also not straightforward. What speed do you use in the tool and what kind of tool you use, it requires a little bit of know-how. So you can't take a part that is printed, go on and finish it at a CNC shop or a machine shop without expecting to waste a couple of parts until they learn how to process it. This is the tool in operation. Again, what happens is that the customer used the first tool to test it, and then after 6 months, they replaced all the other tools with it. This is how fast the tool is going, and that's why the weight was very important. Doing it out of a metal block was not feasible at all. This is another example of another tool. What we did over here was, again, the central block over there was already given because they have many other machines that had that block. So they didn't want to redesign it. And then what we did is just build the 2 towers. Again, the length was too high, and the challenge with this one that we're getting deflection. We use the load case we use for robots. The worst case is the E-stop. The E-stop gives about 6G of acceleration, and that is the worst condition where a component can observe on a robot. In that case, we allow the tool to deflect by 10 mil or 15 mil. So we don't care in an E-stop that it doesn't deflect. But in operation, in the operating condition, we then limit it to half a mil, or depends on the application if it's more critical. So then we have 2 sets of analysis, one done for the tool in a crash load, and another one for the tool when it's in operation. In this case, we had to do some reinforcement because we couldn't add enough plastic to make it not deflect more than 10 mil under the E-stop. So we ended up putting tubes inside it to give us some reinforcement. So we just build cavities in, we press fit some tubes, lock them in, and give us the strength we're looking for. In many cases, we do use inner channels. So for example, this is an application where we have a suction cup underneath, and we have an ejector. It needs compressed air coming from the robot, and it delivers vacuum at one of the channels. Normally, if you buy it off the shelf, there is a standard component, aluminum with holes in it and metal fittings, and you put the ejector and you get your thing done. In our case, we just use the 3D printing to create inner channels to supply the compressed air, and we do have lots of applications for compressed air manifolds. And then we have the suction cup mounted underneath. It's all integrated, much lighter, and it's one component. You have everything embedded in it. This is probably 40 or 50% of our applications involves some sort of a suction cup and ejectors in it. These are the tools, the 2 tools that we developed. They were done for ABB. They were trying to showcase the technology in one of the robots, and this is the. These are the robots picking, one for 2 suction cups, and one was picking 1 suction cup. This was just a demo that they used in their trade shows. This is a little bit more complicated one. One of the recent ones we did about 6 months ago. It's basically they pick from a position and they spread, drop in another position. So they pick from the products next to each other. They pick the product, they spread, and they drop it in the boxes. So here we had, and what over here is the flange where the robot connects. We pick up a rotation from the robot's axis, and then we supply, inside there is a gear that pushes those open and close, and then this gear over here rides at a different speed to push the next round up. So I don't have a video for it. We're having one prepared, but this is how it works. Like you have, it moves in this direction. Just the sliders that you see on here are 3D printed. So this is basically a slider and a carriage that usually you would have you'd buy from McMaster or from any of the hardware companies. They were very heavy. So the block is aluminum, and if I use, actually in this case I'm using 6 of them. They ride on a solid bar, which is very heavy. I didn't have that much luxury to use the standard components. So we ended up getting a standard aluminum extruder profile. We got some tiny little bearings. We printed some wheels with the right profile that matches the profile we had, pressed them in, assembled it. We added a feature here with an M2 where you can go in and adjust it for the pressure on the preload. And there you go. So we had 8 bearings in different directions of it. And then we custom the bottom of it to match with what we need to do. And then we build the towers. This is a quick connect. So you click open, you take it out, put another one in. We needed to do that because those ejectors used to block from the dust in the plant, and they didn't have time to take it off and clean it. So we built a set of spares. We just click them up, put new ones in, and get started, take them in the shop and clean them. This kind of flexibilities are not available in the market. You go out, you cannot buy this elsewhere, or you cannot buy this from McMaster or from any other. It doesn't exist. But when you have an ability to design and build in 3D printing, you can make them yourself. It is not straightforward. It needs a learning curve. And the companies who succeeded were the ones who were patient. Because some people would come and say, we're going to use this technology. Their expectations are the same as a CNC. They expect 10 microns or 2 microns. It's not. They expected the flatness. You don't have flatness there. You have warpage. It's part of the technology. It's not a roadblock as long as you understand it, you know how to deal with it. You know how to design for it. You know what to expect from it, and so on. So that's why you need to use it, but be patient at the beginning until you learn how to use it. This was the first tool we used. I believe the video here, I tried it before, it was not working, and it's still not working. So that is the same concept of the tool, but we designed it originally with the standard components. We used iJust sliders. We said, well, let's go for the standard. iJust was the lightest sliders. We used the sliders. It didn't work. 40 hours later during the testing, it just started ceasing to work because the two guides had to be they had to be parallel, and any small movement, the robot hits anything on its way, or somebody squeezes on the two guides, they are no longer very parallel, so they get jammed. So the loads then increased. It wasn't working very well. That's why we took it off and we developed the other one with our own sliders. So we didn't go and say, well, let's use 3D printing because it's cool. We first started using standard components, and when we saw that there's an opportunity, we can do better with 3D printing, we ended up using 3D printing. It took us from that tool to the second tool 10 days, 1 week of design and manufacturing. So 10 days, complete different way of support, including the development of the sliders, 10 days. This is another tool where we have, these are bottle grippers. A machine that we're going to see in the next video picks grippers and put them, bottles, alcohol bottles, wine bottles, put them into cartons. sorry. So that was a video during the company is EFA, so I got this from their website, so I'm allowed to share. I have many other applications that I wish I could share with you, but I have to wait for the opportunity where the customer allows us to share the video, or they put it in public themselves so I can use the video. So basically, those are the belly dancers. They go in around. They're cam driven, and then you push on the arm, it goes down, and inside there are two tubes that have a bunch of links that go and wrap around the bottle. So you see they come down, pick the bottle, come out at 300 bottles a minute. These are all 3D printed, and this is the core of the machine. Everything leads to that moment where you pick the bottle and put it in the box. The rest is all traditional. So we have applications for, I'm a few minutes over, for injection molding. This is an application where a customer, they use the flasher. So they have the bottles are coming out of the mold. They need to have a punch to take out of the excess plastic that comes out. They need to hug the bottle with the same profile. In every project they have a different profile of a bottle they have to take care of. They used to mold those. So those they take a bottle, they put it in and they make a mold around it, they cut it in pieces, they machine it. That's what this is ancient, this is something new. So we first talked to them about it, they say, well, this kind of things are very tough. There's a punch with a very big cylinder, come in and punch the bottles around it, and it's not gonna work. We cannot use these plastic parts for that thing. So we said, let's do the analysis. So we took it, we applied the loads. We found that the load is only around that part, because that's where all the load transfer is. Beyond that is just, there's nothing going on. So simulation showed where this area is, we reinforced that part, and now that became the standard way of doing it. They now do the design themselves. So the first 5, 6 applications, we did the design for them. Now they learned how to do it, how to keep the weight down, how to keep the cost down, and now they're doing the designs and just, they get the bottle, they scan it sometimes, or they have the file, they create this model, send it to us. 3 days later, they this is another application where they need to pick the bottles after the line is done. They come in rows, they want to put them in cartons. Notice that we've built it in 3 parts. So this is 2 manifolds, taking the profile of the bottle to make sure it stabilizes it. And then because we have a bed that is 30 centimeters, we can build only within that range. So we had to build it in 3 components. A central component, and then attach 2 sides of it, put some screws, held them together. So we use lots of hardware, traditional hardware to build our parts. This is another one that is for injection molding for automotive. Again, it's very large. You notice the center flange, and then 2 left and right. You notice the complexity of the geometry, again, topography optimized, same as the concept we explained. The grippers you see over here, those grippers here were printed because the standard ones off the shelf were very heavy, and they are sitting on the very extreme sides of the tool. When we put them in the model, they were causing us to add too much material to support them with the inertia and the speed. So we said, well, we can get tiny little cylinders and then build our own gripper. So this is what we did. We're just taking out very light piece of plastic, so there's no need for this heavy-duty gripper. So that's what we did in this case. Other application for injection molding. Every little suction cup here is picking up a part. These are 4 channels of air connected together internally, and then suction cups are just connected to it. Different cases, we do that almost every month, 2 or 3 of those going out to one of the vendors. This is another application for picking a very delicate part from an injection molding. This was a traditional tool originally. This was one of the very first tools we built in injection molding. And then we ended up building a set of tools for it that have the exact profile of the part and goes in and have a vacuum manifold, picks the part in, and then grab it with grippers. Again, these are 2 arms that wrap around the part after it comes out of the mold. We have also applications for manifolds. These are larger size manifold. You notice this, the way it's broken down to pieces so that we can fit in the machine. So a central core, and then you have segments around it, and then we assemble them together with screws. We have a seal around, and we put a standard plate underneath. This one is in operation. I'll speed it up a little bit because it takes a while to get the bottles in place. And then this is a manifold, has air connected to it, and then comes, picks the bottles with, applies vacuum, picks the bottles, put them in a box. So we have done a large number of those manifolds, and right now we're building one for a complete pelletizer with 70 kilograms weight. We're going to be holding 70 kilograms of weight with these plastic manifolds. So right now this one is in development, and I think this will be a very useful product because the weight would be 1/3 of the traditional metal one. Other manifolds, again, for different products. That was for 3M. The air is sucked from here. This is the quick connect tradition we use. These are some blow-off valves, and then the rest is underneath are just holes and the pattern of holes. We also do overmolding, where we need to have a contact between the parts and the Class A surfaces in automotive. We cannot connect with nylon. We need to have types of urethane to connect with. So that's why we use overmolding. So basically, we build a part in plastic, and we create a mold with that geometry, also out of plastic, and we pour cold molding, and basically the urethane sticks to the nylon. We've done this. There's another application I couldn't bring with me is for Toyota. It's a door nest. It's the inner panel of a door panel. To assemble it is an assembly nest. So basically, we have 3 sections. Each segment, the 3 of them makes up a door. And there are 16 of them on the line. And they needed for the first time to do it lightweight because they want to have changeover. Usually those are sitting on a conveyor, and they don't move until the model is retooled. The line is retooled for a new model. This time they wanted to use the same lines, but they wanted to have a light application. So we ended up building those segments mounted on have an internal core of foam, which we built foam molds for it. We used the foam molds to create the inner structure of the door in foam, and then we created another plastic mold for the same method here to have the outside surface. We built about 4 lines. Each line had 16 doors. Each door has 3 panels, so you make the math close to 200 panels. These are some applications for check fixtures. Check fixtures where we have usually every plastic part in every car needs to have a check fixture where they have they measure the dimensions of the part. They want to move to scanning. So instead of having to have physical measurement, they want to take the part into a fixture into the scanner. So now the fixture needs to be light. So what we did is that we had a hybrid solution where we had a backing plate made out of traditional flat plate with supports, and then we used the same topography optimization to come up with the geometries required, only had material where we needed, and then those surfaces to get to the accuracy had to be machined. So after it's all assembled like this, we leave excess material 5-6 mil off on top of it, and then we just go phase them off. The overall cost is much cheaper than traditional, probably half the price of the traditional tool, and the weight obviously is much more manageable. These are applications for sand casting. Again, I couldn't bring the full parts because of confidentiality, but sand casting is one of the applications we do. We don't do much of it because the industry is still very traditional. It's very hard to get them to accept new technologies and ancient technologies. So we haven't had many of them, but we are capable of producing them. That's about it. These are the machines. These are the batches. When they're prepared, they are, you can pack quite a bit in a batch. That's why we can make cost-effective products with this technology. That's about it. Sorry for taking longer.
Well, we were late started, so that's